All right, so not much in the way of announcements for today. Um, as you can see, I mean, we're kind of in between steps right now. We just finished all of our Chapter 2 materials last night. As far as the grading of those quizzes goes, I'll try to have them done today. No guarantees on that. Hopefully, I'll get them to you before we meet again on Monday. Um, so I'll get those to you as quickly as I can. Similarly to what we saw in the Chapter 1 quizzes, some of the calculation-based stuff is kind of fickle with the significant figures. So what you initially see as your score might adjust in the upward direction if you did something like put in 4 significant figures instead of 5 or something like that. So we'll address that as it comes. But like I said, as far as the questions on that quiz go, most of them were auto-graded. There was the one essay question that you had to deal with. So I will be getting those hopefully out soon so you can just have a preliminary score, and then if any adjustments are made, I'll let you know. Other things, really only 2 assignments for this weekend. The ions proficiency, Sunday in Blackboard, and the post-lecture over the Bohr model of the atom in grade scope. Those are the only 2 assignments over the weekend. We will be continuing with Chapter 3 for all of next week. As we go through getting into more of the quantum mechanics, more of the explanation of electrons, and then eventually the periodic trends. So, any questions about our schedule before we get started? So if you recall from our class on Wednesday, we ended with the concept of the photoelectric effect. We watched that kind of campy Lonnie's Lab video about the impacts of the photoelectric effect. And we kind of ended on a cliffhanger where we left the scene in 1905 in Germany, and a patent clerk by the name of Albert Einstein. And so what Albert Einstein does is he starts to put together some of the things that are known. One of the things that he puts together is the idea of Planck's work, the idea of energy of light. And he rationalizes something called a threshold frequency. That is a minimum frequency of light, a maximum wavelength of light, if you will, where those electrons would be ejected. Now, we saw that threshold frequency in the photoelectric effect video with the yellow filter. Because if you remember with the yellow filter, they shone the light through the yellow filter, only yellow photons were being transmitted. And as a result, what did we see? Well, we saw that the multimeter barely moved off of 0. The electrons were ejected, but they didn't have a whole lot of energy. That's the idea of a threshold frequency. Threshold frequency is the minimum amount of energy, the minimum frequency, the maximum wavelength, however you want to look at it, of light that would actually eject an electron. And those photo ejections are small, barely get out of the atom kind of ejections. And then what we saw in the others, the green light, the blue light, is that those higher frequency, lower wavelength, higher energy, they ejected electrons as well. But not only did they eject electrons, they ejected electrons with higher energy. Kind of think of it as you're rolling two balls against each other. If you just gently roll one of those balls, and it bumps another ball, and it gets that other ball to move to the other side of the table, but it does so really slowly, and it really doesn't have a whole lot of energy. That's kind of like your threshold frequency. The aim is to get the ball from one side of the room to the other using the other ball as a bouncing target. There's a minimum amount of energy that you have to put in to get that ball to move across the room. But if you throw the ball harder, it's going to reach the same aim. The ball's going to hit the other ball, go across the room. The difference is how much energy that second ball has once the collision occurs. The more energy you put in, the more energy comes into the second ball. You know, think of it the same way, you ever seen one of those Newton's cradles? The ball bearings on the string, and they click, and they move on. Well, if you move that ball just a little bit off of this cradle and let go of it, what happens? Energy comes through on the other side, the ball on the other side gets ejected a little bit. If you raise it up really high, it comes off really high. It's the same kind of idea. Once we hit that minimum frequency, that minimum amount of energy to get the electron out, any energy that is left over just gets put into the speed, the energy that is in the electron once it is ejected. So this covers the idea of electrons being able to move. How does that ultimately relate to what we were talking about on Wednesday, the spectral lines? Where does that idea come from? And so we have to integrate another series of ideas here. And for this, we're going to look specifically at the hydrogen spectrum. So we're going to focus primarily on hydrogen and its reactions, its interactions inside of the nucleus, or inside of the atom. And so what the Balmer series ultimately focused on was we were looking at hydrogen, and in particular, we were looking at those four spectral lines inside of hydrogen that showed up in the visible part of the electromagnetic spectrum. You may recall we showed you this spectrum on Wednesday. There were four spectral lines in that hydrogen spectrum. And so this is what the Balmer series was discussing. How do we quantify, how do we measure, how do we explain those four frequencies, those four energies, those four wavelengths of light? And to do that, we use something called the Rydberg equation. So Balmer and Rydberg both worked with the hydrogen spectrum. Balmer focused on the visible light portion of the spectrum for hydrogen. Rydberg actually focused on what we would call the ultraviolet part of the spectrum. And the Rydberg equation is the result of their work. What they were able to determine is that if we think about an atom and the electrons in that atom as existing in these energy levels. So there I've got my nucleus, and around that nucleus I've got these energy levels, kind of like orbits around the sun. This is one of the early influences of the Bohr model of the atom, was on the planetary model. But if we look at it from this perspective, and we label these so starting at the bottom here, we have the first energy level, n equals 1. Here we have the second energy level, n equals 2. Third energy level, n equals 3. The fourth energy level, n equals 4. And the fifth energy level here, n equals 5. Now, technically speaking, under the Bohr model of the atom, n, the energy level, can actually go about as high as you can count. One issue with the model, at least the way I drew it, is that it was widely theorized and is still held true today that those energy levels are not evenly spaced apart in terms of their energy. In fact, the energy gap between the first energy level and the second energy level is the biggest. The energy gap between the second and the third is the next biggest. And they get smaller and smaller, and the energy levels get closer and closer together as you go out further and further away. To the point where when n is equal to infinity, we consider that electron to be gone, lost. And so this actually is what is used to help us figure out threshold frequencies. Because if we know that an electron is in the second energy level, and it is going to the infinite energy level, the Rydberg equation actually helps us to predict what the wavelength of light would be to get such a transition to take place. So the Rydberg equation gives us a general equation for predicting wavelengths associated with given transitions. Now keep in mind, we're still talking about quantization here. So the energy gap between energy level 1 and energy level 2 is a specified amount of energy. And the energy level gap between energy level 2 and energy level 3 is a specified amount of energy, which means only one wavelength will actually allow that transition to take place. Now, what the Rydberg equation does is it helps us to predict something called a wave number. Wave numbers are nothing complicated. They are just applications of the reciprocal of a wavelength, 1 over wavelength. So wave numbers are given in units of meters to the -1, or 1 over meters. To find the wavelength, we just take the reciprocal of the wave number to figure out what the resonant frequency is. And so when we use this equation, a couple of things to point out. RH is something called the Rydberg constant. The Rydberg constant is 1.097 times 10 to the 7th wave numbers, reciprocal meters. This equation covers any transition of energy. So N1 here would be our starting energy level. N2 would be our final energy level. One thing about the sign convention here, a negative value would mean that the wavelength is released. So this would be an emission. A positive value here would mean that the wavelength is absorbed. So this would be an absorption. So, and this should make sense, right? If my starting energy level is 1 and my ending energy level is 2, that would require an absorption of energy to jump up in energy level. 1 over 1 is 1. 1 over 2 squared is 4. I get a value out of that subtraction of 3/4, a positive number, which would mean a positive wavelength. Energy is being absorbed at that particular wavelength to graduate that electron from the first energy level to the second. If the reverse were true, the subtraction would come out negative, and it wouldn't mean that we have a negative energy or a negative wavelength, because no such thing exists. It would just mean that the wavelength of light was emitted instead of absorbed. So sign convention becomes very, very important in certain fields because a negative number does not always mean what we traditionally associate with negative. Sometimes it is a convention that tells us direction. And that's the case in this instance. Negative and positive tell us the direction of the energy. Is the energy coming in? Then it's positive. Is the energy going out? Then it's negative. Okay. What is the wavelength in nanometers of the line in the hydrogen spectrum that corresponds to a transition between the second and fourth energy levels? We're going to use our Rydberg equation for this. So 1 over lambda is equal to RH multiplied by 1 over, we're starting at the fourth, so 4 squared minus 1 over 2 squared. (1.097) times 10 to the 7th reciprocal meters multiplied by the difference of 1/16 minus 1/4. 1/16 minus 1/4 is going to give me negative 3/16 as a result of that subtraction. Negative 3/16 times the Rydberg constant, 1.097 times 10 to the 7th. I get a wave number of, to four significant figures, negative 2.05700 reciprocal meters. So we're talking about 2.057 million wave numbers. To flip this fraction around, you're going to look for the button on your calculator that either says 1 over x or x to the negative 1. That's going to take the reciprocal. That gives me negative 4.862 times 10 to the negative 7th meters. To turn meters into nanometers, I multiply by 10 to the 9th. And that would give me 486.2 nanometers. And again, the negative there is referring to the direction of the energy. This is an emission. If an electron goes from the fourth energy level down to the second energy level, it is going to give off light because of the difference of the energy between the two levels. Higher energy levels mean that the electrons are at higher energy. So when they go from a higher energy level to a lower energy level, they're going to give up that excess energy that exists between them. We see that as light, heat, sound, a variety of different energy forms. In this particular case, it's ejected as a photon of light. Right, any questions so far? All right, try this one on your own. What is the wavelength in nanometers for a transition between the first and fifth energy levels in the hydrogen atom? And then secondly, how much energy would need to be absorbed for such a transition to occur? So take a couple minutes and work on that. I'll come around and see how you're doing. So walking around, most of you got the wavelength part, or at least got close. You should have come out around the neighborhood of 95 nanometers for the wavelength. If you carried the sig figs correctly, it would have been 94.96. For the second one, this is the kind of calculation we were doing at the beginning of Wednesday. Can you take a wavelength and turn it into energy? Or can you take a frequency and turn it into energy? And the answer is yes, if you use the Planck equation. For wavelength, energy is equal to Planck's constant, h, multiplied by the speed of light, c, divided by the wavelength lambda. And if you had done that, you would have got 2.092 times 10 to the negative 18th joules. So thus far, all that we've really done, we've talked about another way of viewing the atom. We've kind of brought in the concept of the Bohr model of the atom, where we've got those energy levels that are present. Now we need to kind of ramp it up a notch here and start using the two concepts together to explain why those atomic spectra appear the way that they do. All right, any questions about this example problem? So let's summarize a little bit. Based on the first day and a half here in chapter 3, we can make the following conclusions. First of all, we can understand that the electrons that are in the atom exist at specific energies. That's the whole concept of quantization. An electron exists and has a certain energy in that atom. And when it moves from one energy level to another, it either gains energy or loses energy, but still has some quantified amount of energy associated with it. To move from one energy level to another, it's going to have to gain the exact amount of energy to go from one energy level to the next. And when it goes down in energy, it's going to release that exact difference in the energies between the two energy levels that it travels between. And then finally, the Rydberg equation allows us to predict the wavelength. And with the wavelength, we can also find out the frequency and energy using those equations from Monday. For any electronic transition that exists between hydrogen atoms or any other atom that is of a single electron origin. So if I have helium and I've taken one electron away from it so that it only has one electron left, the Rydberg equation would predict its spectral lines. If I took lithium and took 2 electrons away from it, made lithium 2+, 1 electron in total, the Rydberg equation would predict its spectral lines. And so this entire concept gives us an idea of what we would call the Bohr model of the atom. And so your post lecture for this weekend focuses a lot more detailed on the Bohr model of the atom. But the idea is relatively simple. As I mentioned before, the idea of the Bohr model is I've got my nucleus here in the middle, and I've got my energy levels existing in these kind of planetary-like rings. Around that nucleus. And as far as this is concerned, this is what we look at. Now, hydrogen atom, we've got the electron moving around in that circular motion, following the orbit around that energy level. When it's in that energy level and it's orbiting around that nucleus, it's going to have a constant energy. We integrate quantization here by talking about the fact that there are orbits that are allowed and orbits that are not allowed. Only certain orbits are allowed. We can only transition between one orbit and another. each orbit has a specific value, again, quantization, a specific value of angular momentum and therefore energy. And you can transition between the orbits, provided that you absorb or emit a photon of energy equal to the amount of energy that is different between the two orbits. And so that's what Bohr's model, the planetary model of the atom, as it is sometimes called, those were the central assumptions of that model. And for the most part, there are a lot of good things in this model. This is a model of the atom that we largely recognize. Most people, when they think atom, have a vision of some kind in their head related to this, where they've got nucleus in the middle and these orbits of electrons flying around that nucleus. That being said, the Bohr model of the atom is not all that it's cracked up to be either. It has survived because it's pretty easy to digest. It's pretty easy. We already have a planetary model in which we teach our children about the solar system. You all know it well. And it makes sense. And from that perspective, viewing atoms in this similar way also makes a lot of sense. But when we get down to the nitty-gritties, when we start to actually examine the quantum mechanics and some of the things that were going on in that time, again, we're talking early 1900s here, we do run into some problems. So what are some of the strengths of the Bohr model? Well, one of the things that the Bohr model allows us to do is, using that Rydberg equation, we can pretty accurately predict how much energy it's going to take to remove an electron from the nucleus. We call that process overall ionization. Another real strength is that it gave us a starting point. So unlike the plum pudding model, which was kind of a healthy guess, but it was a very uneducated guess, given that we knew so little about subatomic particles at the time. And the Rutherfordian model that came after it, again, good for its time, but lacking a lot of detail. Now we've got something that we can really sink our teeth into, and it really does explain well some of those quantum phenomenon that were really troubling the physicists of their time. Where it had its limitations, however, it only worked for hydrogen. The Rydberg equation only works for hydrogen and for hydrogen-like ions. That is, ions that contain one and only one electron. The other big thing here that is a big limitation, how electrons move inside of the atom is not nearly as defined as what Bohr was describing. They don't just move around in these circular orbits. To really, truly, fully understand what was going on and to try to explain it, we needed to integrate even more quantum mechanics than what we already have. And one of the things that we had to do is we had to dispense with the idea that electrons are just simply particles. Long about 1920 or so, we start to get into this idea of the dualism of electrons. So the photoelectric effect gave us the idea that light has a dualistic nature. We talked about light in terms of its wave-like properties. It has a wavelength, it has a frequency. When we got into Planck, we saw that photon had particulate kinds of properties as well. We can think about photons as these packets of energy that, although they were massless, they had the capability of knocking electrons around inside of that atom. So we have a particle property of light in its energy, its momentum, and the relationship between its frequency and those kinds of properties. Now we start to see with electrons that electrons have dualistic properties as well. Electrons actually can behave as waves, matter waves. Now, there were lots of theories. There are lots of people that kind of worked and kind of cobbled this together. James Clerk Maxwell and Albert Einstein are given primary credit. I'll save you the biography on Maxwell. I'll leave that to any physics course that you take. Physicists love Clerk Maxwell. He kind of wrote the book on most modern physics, or at least a good chunk of it. But this dualistic nature of electrons does give some rise to some issues in the Bohr model that we need to ultimately explain away. And one of those gets explained by a man by the name of Louis de Broglie. De Broglie kind of takes it to the ultimate extreme. Not only are electrons dualistic, all matter, in fact, has a dualistic nature to it. All matter exists in particle form, which is what we familiarize ourselves as. Takes up space, has mass. But also as waves as well. Any object in motion does emit a characteristic wavelength. The question is, what is that wavelength? And so the de Broglie equation tells us what the wavelength is relative to an object's mass and an object's speed. The wavelength of any particle is equal to Planck's constant h divided by its mass in kilograms and its speed in meters per second. So what that means is that you and I, we both have waves. When we move, we are emitting characteristic waves. However, our mass and our speed kind of dwarf out and make the matter wave that we are emitting practically negligible. If you do the math on it, you end up with a wavelength of like 10 to the negative 35th, 38th, when it comes time to actually measure your matter wave. At that wavelength, that's practically zero. You have no real waves coming off of you. But for objects that are small, like electrons, where their kilogram masses are on the order of 10 to the negative 27th kilograms, their characteristic wavelengths are actually real and important and make a difference in terms of how we view them and ultimately how they interact with the world around them. And so we're going to end today by watching another snippet of a Professor Dave. To get into the big time issue here, ultimately, particle wave duality has a lot of aspects to it, a lot of dimensions to it. We ultimately need some pretty high-end calculus to solve it. Obviously, we're not going to get into that in this class. But the central tenet, the thing that we're really interested in, we can definitely get behind. And so I'm going to shift over, hopefully.
Do you need that equation that pops up on the video then?
No, you do not need the Schrodinger equation. Let's see if
Through the work of Planck and Einstein, we were forced to accept that energy is quantized, and that light exhibits wave-particle duality. Then de Broglie extended this duality to include matter as well, meaning that all matter has a wavelength, from a tiny electron to your whole body to a massive star. However, an object's wavelength is inversely proportional to its mass. So objects bigger than a molecule have a wavelength that is so tiny that it is completely negligible. But an electron is incredibly small, so small that its wavelength is indeed relevant, being around the size of an atom. So we must view electrons as both particles and waves from now on. Therefore, we must discuss the wave nature of the electron. So what kind of wave might this be? We can regard an electron in an atom as a standing wave, just like the kind we learned about in classical physics. Except that rather than something like a plucked guitar string, an electron is a circular standing wave surrounding the nucleus. If we understand this, it becomes immediately apparent why quantization of energy applies to the electron. Because any circular standing wave must have an integer number of wavelengths in order to exist. Given that an increasing number of wavelengths means more energy carried by the wave, we can see the Bohr model for the hydrogen atom begin to emerge as we imagine a standing wave with one wavelength, and then two, and then three, and so forth. This is the reason that an electron in an atom can only inhabit a discrete set of energy levels. The circular standing wave that represents the electron can only have an integer number of wavelengths. When an electron is struck by a photon of a particular energy, this energy is absorbed, promoting the electron to a higher energy state and increasing the number of wavelengths contained within the standing wave. This is why the electron goes to inhabit a higher energy level, and this is what is fundamentally occurring during electron excitation. Furthermore, it is the constructive interference of these standing waves that explains how orbital overlap
and we're really not ready for the rest of this. So I'll leave it at that. Hopefully the visualization there kind of gives you a better picture. We'll talk a little bit more about this in our virtual session on Monday. Have a great weekend.